The last address here, you can see, is a club, a robotics club, where we have hackathons and we share code that is made during these hackathons. For example, cocktail machine that could be, you can order your cocktails using mobile or something. Yeah. So, I'll start with this, that my idea was simple, but after some thinking, I was thinking that robotic programming should not be something low level. It should be according to the high level standards in order to be easy to maintain and to be easy to use from other people. And different people can extend different parts of the software, for example, providing additional services for additional sensors or actuators of the robots and IoT devices. That's why I started domain-driven design. And after that, about services, but very lightweight of services, which are actually producers and consumers, separating concerns between commands and receiving, publishing data to multiple devices or screens or displays or mobile applications and other clients. After that, I'll go to iterative to reactive. What's the difference and what are the advantages of reactive programming in Java, and especially for IoT and robotics case. They can run on even Raspberry Pi and Lego. And after that, I'll go to some code, and I have, of course, all the code in the GitHub. So if you're interested, everything is public. Okay, this will be the idea. We start with this, that not everywhere, people were evolving recently towards computers and computer-based interaction. But actually, this made our lives not so simple. We have better tools, but to cope with more complex tasks. But tasks become even more complex, and tools become even more complex. So, where is the end? Where is the limit? And how you can manage all this complexity? And domain-driven design is one such modeling approach that tries to use abstractions that are domain-driven, that are actually the domain objects that everybody knows. Every stakeholder, every manager, every student that does some robotic programming should know the basic concepts in this area. For example, what is motor, what is servo, what is ultrasound distance sensor. These are the domain objects in our small robotic world. But of course, this robotic world could be coupled with other worlds, with a world of service-oriented architecture or microservices, and so on. And this data could go to the cloud, could be hosted in different services. And that's why we need to separate concerns. We need to have our small robotic programming in our small robotic domain and keep service-oriented programming, server-side programming on the server-side domain or mobile interaction using appropriate terminology and appropriate ubiquitous language, if I pronounce it correctly. So this is the main idea, that we separate our concerns to bounded contexts that are small with well-defined limits, boundaries. This is the actual idea that is not new at all. In artificial intelligence world, it's called intelligent agent. What's intelligent agent? It's problem solver, but in bounded context. This is not a new idea. It may be new for the whole community, but it's not new, at least for artificial intelligence community. To try to solve the problems in small, in bounded contexts, bounded rationality. How we do this? First of all, in order to have separation of concerns, we introduce even more concerns. This is normal. In most of the modeling approaches, you have to do some work in order to make a separation clean. you have to provide clean interfaces. And here, in domain-driven design, we have 4 layers, excuse me, infrastructure layer, which may be, for example, some robotic low-level services or some general services in case of other domains and applications, for example, PDF conversion. Domain services are is the place where our domain objects are sitting and our domain services are implemented. Some of them are implemented also in infrastructure level. Application level integrates different subdomains or bounded contexts in something usable from user perspective, an application. And the presentation layer gives view to this application, to this functionality, useful functionality to the outer world, using the hexagonal architecture, which I didn't have place to draw, but this is the simplified drawing. You can imagine it like a hexagon with different sides representing different types of interfaces. Internal, external, to message-oriented clients and event bus, to REST-oriented outer world. So we need, of course, transformation of the language or our APIs and domain objects in their shape in order each community to be happy with the domain terminology. And that's why we need the transformance and the entrance of our domain application. Okay. Other artifacts in domain-driven design are entities, value objects, and modules, which here I actually didn't have any entity because all the data is immutable and is processed stream-oriented through transformation of immutable objects. Actually, in this particular example, we will not have entities because the data is short-lived. Of course, there are different possibilities to model, but entities are some objects that have continuity of state, while value objects are something that is just immutable representation of some values, resource representation, for example, in REST terms. And we have also services. Particular types of services are repositories and factories, which are recommended to aim domain-driven design to create our different artifacts, not to have direct dependency, in order to easily extend our, and test also our designs. And of course, there should be separation between interface of factories and implementations and services also. Let's go. The next interesting theme, which is quite modern, is separation of concerns between commands and queries. And here are some differences which we can see in different type of operations. Why? Because queries do not need transactions. They're happy with eventual consistency. They are even more happy if database is just a map, a denormalized, for example, database. And also, they're even more happy if the views could be just out of the box, automatically created using the data objects, the domain objects, which is the idea behind naked object or material views, materialized views maybe. So the commands are the other side. They're most of the time transactional. Eventual consistency is not the easiest way to do them. They have to care about having unified picture of the world, because you cannot sell the same product to two different persons if there is only one. And these are the requirements of commands. That's why we want to separate them. How we can do this? We can do this in different types of services, for example. There may be services that are reporting services and services that are update state services that are updating the state of the application, which could be handled differently using different databases. And for synchronization, for example, event sourcing could be used. All the events that are done or serialized just as events, not as states, and shared between different participants. That's the way they could achieve consistency eventually. And also, you have the full accounting of what have happened. You can go to the particular state from the very beginning and you know everything. That's the good parts about event sourcing. So I'll go to the next topic, which is the imperative versus reactive. So what's the main difference? The main difference in reactive programming is, first, it's more natural way, because everything we are looking around is reactive. If something happens, it continuously have some ripple of effect to different things. So you can change something, but the effects are immediately propagating to other things. And this is the way the nature works. The separation, the iterative way of modeling the things is actually something maybe more simple for us as programmers, but it's not more natural. So we live in a connected universe, and actually this universe, there may be hypothesis that it works on a reactive way. Something happens and everything other is changed automatically. No specific cycle or iteration needed. Okay, so these are some ideas about what reactive programming is. If we have imperative programming, we have B and C, we have some values. A is computed once, and after we change the B, A is not changed automatically. In a reactive world, if B is changed, A is automatically changed. So every change in the input is automatically propagated to dependent variables, so, called sometimes data binding. Okay, the next one is what is functional programming. Functional programming also have very good qualities, properties for us, because it allows us to have programming without side effects. You can compose functions in a predictable way. And you know exactly what function does. It could not do different things if the data is the same and the function is the same. So they are easily composable in order to make different transformations of the data. And that is the idea, marrying these two concepts and making a functional reactive programming, which was first coined as a term, I think, by Connell Elliott in 90s. And there are actually two main parts of the definition, what's functional reactive programming. This is denotative semantics and temporally continuous. By denotative, it means that the functions could be composed side effects free. For example, if you have some data that could have null values, you cannot compose this data easily. Because if it's null, you cannot call the next operation on null. That's why we may have something that lifts this value to another level, that we can have objects that could have value or could be null. But these objects are always present, and you can compose operations of them. For example, optional in Java. Okay, so the temporal continuity means that changes are automatically propagated. This was first used for animations that were interactive. So changing something in some controls changes automatically the animation without any programming additional, just specifying the functional links between different elements. Functional dependencies. And here are some initiatives, for example, Reactive Manifesto, which there are many different frameworks participating, but the idea is that we want applications that are resilient, elastic, message-driven, and responsive. Message-driven is the foundation to achieve this. I'm not going into details. If you're interested, you may go and see more. Some implementation of this idea. Reactive programming are maybe one of the earliest is Microsoft Reactive Extensions. You can see an impressive list of frameworks and platforms that are supported with the same functionality, the same language. Actually, it's like learning a foreign language. We know how to do iterations or if-else, switch case, and so on. We know the basic algorithmic constructions, but it's actually not so usable in the functional representation of the processing as transformation of event streams or messages. And it's like learning a new language. And we may say that reactive extensions is quite fluent language for using functional reactive programming. And actually, the same language was implemented in Reactor, in Spring Reactor, which is the actual project which I use for the demo. But the same operations, the same language you can learn and you can use on all different platforms, independent if you're on JavaScript, on Java, or C# or what you want. There is for Netty also, for Android and for iOS. The second one, which I mentioned, is implementation of reactive streams, which is the Spring project Reactor. They didn't market it as Spring, but now it's a quite fast-changing project. Half a year before, the API was completely different. My previous project has nothing in common with my next one project using Spring Reactor. It's moving very fast. There is documentation, but of course there may be better documentation. And they're supported by Pivotal. That's why I call them Spring Reactor. And they started as Spring of Spring also, of course. Okay, so they're used also by some APIs in Spring Framework. For example, big data, I think. So, what are reactive streams? Reactive streams are actually a very simple specification. The idea is to make the things simpler, as simple as possible, but to have some very good properties in order to satisfy reactive manifesto. This elasticity, this fault tolerance, and this non-blocking interaction, high efficiency. How can they be achieved? For example, they can be achieved by not blocking the consumers and producers. We know we may use a queue that separates blocking queue producers and consumers, but we may not use such a queue. We may have a single-threaded interaction without any blocking, just by allowing the consumer to ask for some data before sending the data to the consumer, which is called back pressure. So the back pressure is built-in mechanism, which allows everything to happen if we want in a single thread, but there may be also, as you can see, different implementations using more threads, and again, non-blocking using disruptor, LMAX disruptor or ring buffer, non-blocking concurrency implementation. And does anybody program using ring buffer, disruptor, or non-blocking concurrency? And what is your experience? Is it easy, or?
It's different than normal programming. You have to think differently to use asynchronous APIs, and also Elix Java is a bit different, let's say.
Yeah, 80% of efforts optimizing 20% or 10%, of course. Yeah, but the idea is that it's not very easy to do it if you have to do it many times. And what Reactor provides is a higher level abstraction. So there are different types of streams. Now they can call them differently from previous release. They call them fluxes and monos. And there's also fluxion, which is like flux, but it is more fluent and more RX Java-like. So we have actually 3 types of streams. Monos are like promises. They are streams that have only one event that could happen or could not happen, depending on, for example, you make asynchronous call to some web service, data may arrive, may have an error, and not have data. And the mono is such actually base for implementation of promise. There is also promise in Reactor. But there are more interesting streams that have more data before they complete. So the main idea behind reactive streams is we have actually 4 types of artifacts. We have publishers, which are the data sources. We have subscribers that can receive data. They're just consumers. And they can use their subscription, which they receive from their subscribing, to cancel if they don't want to receive more, or to ask if they want to receive. Or they can ask unbounded receiving if they're very fast and they don't fear blocking by too much input. But the idea is that you can do this without any blocking because the subscriber asks before can receive something. And processors are combination between publisher and subscriber. They live in between them as a different transformation steps. Different processors, they're publisher and subscriber. They have 2 interfaces. This is the main idea. It's actually single-threaded specification, but Reactor goes ahead and provides some concurrent implementations, non-blocking or blocking. There are different types of processing implementations, processors. Okay, so this is just an idea how may look actual implementation using Erhis Java, the first one. You take 2 of the events because only first 2 are interested for us, and we map them, for example, adding some computations or some enrichment, and after that we consume them by subscribing to the data source or to the stream. At the end is a consumer. And we have the data, the first 2 with the dates. Okay, I'll go fast because we don't have much time. The idea is that Reactor implements this Reactor design pattern, but in a standard way, the reactive stream specification. There is also another pattern, which is called Proactor, which allows us to dispatch completions of different operations on different threads if they're long-lived and they need more time. If you have them on the single thread, they will block that thread and the performance will not be good. Actually, both of them are supported, both patterns, Reactor and Proactor, are supported by Reactor library. And you can see it's quite performant, tens of millions of operations per second, at least what you can see on the Reactor's website. I did not make the tests. But how it is achieved? By using different types of processors, for example, non-blocking ring buffer or LMAX disruptor implementation. But you can choose, you can use different thread pools, you can use what you want. Or you can do them just in a single thread, depending on your concrete needs. And they're mechanically sympathetic. Who knows a mechanical sympathy block? Okay, so this is the idea that it's not so easy to program high-performance Java on Java because there are too many levels, and you have to align all of them in order to achieve high performance, so low latency, for example, in high-frequency trading and so on. And there are some experts, and Martin Thompson is one of them, and he's behind LMAX Disruptor. He's behind also in other implementations. I know at least several companies that he has worked on their message broker implementations and so on. But this is the very good source if you're interested in high-performance Java mechanical sympathy block. And these are some of the good parts. You have very low garbage because this is the idea behind this disruptor, that everything is pre-allocated. And if you don't have other things or separate on other JVMs, you can have very, very low garbage and very big distance between garbage collections, especially major ones. The message passing structures are bounded. We also use end-to-end reactive flows. There is also connectors with different network. For example, this demo uses WebSocket connector, which is accessed by using Reactor net. It was different part. Now it's separate project, IO, Reactor IO. They recently separated actually Reactor on several projects. And it implements this reactive stream specification with back pressure, and it exposes a Fluent API, which is the same API which you have in RxJava. That's why I didn't need all of them, because they have the same API now. But if you want, there is an easy way to integrate RxJava with Reactor if you want to use ReactorNet, Reactor IO, for example, with RxJava Fluent transformations after that. It's up to you. Okay. This is a very hello world example, which shows us how you can use Broadcaster. Is a hot event stream processor, which allows us to send events, for example, using Connext or some other publisher. So we're sending actually 2 events. I don't know if I have something to show. Here. We have 2 events here. And after that, these 2 events are sent. They're scheduled on different scheduler, which is actually a sync scheduler. There are different types of schedulers. A sync scheduler is used for scheduling tasks that are concurrent, but are short-lived. And there is also another type of scheduler, which is used for long-lived IO, for example, tasks. There are different types of schedules, so you can dispatch your computation on different scheduler if you want to. Excuse me, I'll just have my mouse because. Sorry. Okay. So after that, we have some processing, for example, to uppercase, and after that, we have some filtering, which is actually very the same way as we use in Java 8 lambdas, the same operation, but there are a lot of more operations. For example, for hot event streams, there are 2 types of event streams. Event streams that are bounded number, for example, from a collection or from some data source, and event streams that are continuous. They have no number. They are all the time. For IoT, for example, the encoders from the robot. And they are called hot event streams, and they have different properties. For example, you cannot keep them all. Or you can, but you may not want to do this. That's why we have to use some buffering. For example, you may just have some aggregation and have to lower the speed of producing such events. So there are different operations for all these types of computations you may want. And you may specify how many events you want to cache in order to make a certain stream, a hot stream. Because if you have several thousands of events per second, you may not want to keep all of them. You may want to aggregate. Okay. So the next one is Reactor Bus. I actually started my implementation using the bus. The bus provides event bus, high-performant event bus, that allows different type of producers and consumers to subscribe and to send also events. There also may be different message exchange patterns. For example, request response may be implemented easily out of the box using this bus. But this is against, at least this is my opinion, against the idea of separation. And I prefer to use dedicated producers and consumers for different types of events that I'm producing and consuming using domain-driven terminology. Okay, so let's go to the demo. Maybe just to say that, okay, this is the first robot. You can see the robot here. Um, it is based on Lego, and it's standard Lego Mindstorms robot with 3 sensors, which are touch sensor. You can, yeah, here. So now we may go here. This is the touch sensor. This is the sensor for cover, but also we use them with students in order, if you put them on table, not to see when it's out of the table before going actually falling up out of the table. And also he can grasp some objects, cylindrical, and there are other things the robot can do. I can start it, I think, but yeah, maybe later. Just a moment. It didn't start yet. This is a customized power supply, because the power is something that Lego has a very hungry of, and the batteries don't live long. So the main demo is based on this small robot. It's called IPT Pi. IPT is my company. Pi is the same letters but in different. Okay. You see central symmetry. And now I have uploaded, actually I use for development one plugin which is made by Bulgarian. I am proud to say, Cvetan, I don't remember the family exactly, I'll tell you. But it's called LaunchPy, you can find it. And it's a very easy way to upload your Java programs directly on the Pi and to start them. And there is also one commit, which I think is not yet in the master branch. That allows to just upload your Maven artifacts, not all of them every time, because it's not very fast other way, just the difference, the deltas. And I actually use modified version of this LaunchPy plugin to upload my Java programs. I can show, I think here in Eclipse. How can I start this? I can do this in 2 ways. I can start from here by double clicking. Okay, I show you. Yeah. Not so easy. Double click. No. Double click is not my. Maybe I'm. Now. Okay. So execute. Yeah. And it starts very simple interface, but you can don't see this. I'll show you on the mobile application, which has the same shape as the embedded screen. Okay, so I'll start it from the other way, from the LaunchPy, in order to demonstrate the plugins. So what I have here, this is the project. It's on GitHub. You can see where it is. It is on this repository. Sorry. Okay. I have made some change. Okay, now it's okay. So the repository is called Vox Demo, and this is the where it is. Remotes. Here it is. GitHub I product Vox Demo, so you can see the demo. If you want to see the source code. Okay. Maybe here. GitHub, my product. Okay. And the demo is Vox Days. Demo. Here it is, yeah, Vox Demo. And you can see here is the project. It's Apache licensed, and it has 2 parts. The main part is, of course, the Java part. The other part is the Angular 2, excuse me for my Bulgarian. Angular 2 plus RxJS. Actually, Angular 2 uses RxJS as infrastructure, as you may know. And I made my custom WebSocket implementation because they didn't have WebSockets. Or I didn't find it. There was, for Angular 1, such a project, the RX DOM, but for Angular 2, I didn't find it. So I made my custom, I show you, actually. So let's go. Web app is aware the web code which I mentioned. And this is the Angular 2. I can show using Sublime, for example. Okay. The main, yes, TypeScript, yeah. I wouldn't suggest not using TypeScript for Angular 2. Okay, so maybe the most interesting part is WebSocket implementation, which is TypeScript WebSocket, yes, this one. It actually has interface which provides three, it's bidirectional producer and consumer for WebSocket messages, plus two observers, open and close observers that could be registered in a reactive way using RxJava. Actually, everything, RxX, is about observers, observer pattern. And okay, you can see the implementation and also the main application. Here it is. We have two types actually of events, position events, which are consume-only events, or queries, and commands, which are actually quite advanced commands. Not all of them are implemented, but it is odometry, robotic odometry implementation, which is adaptive implementation, which tracks the actual path you specify using these parameters. Delta x and delta y are the vector of your movement, and curvature is the exact curvature of the curve that you want to the robot to follow. And there also is a velocity. There will be also angular velocity and acceleration, but they are not implemented yet. I have actually 4 operations for the demo. These are forward. I can demonstrate that robot. First of all, this robot uses some hardware, which are modified motors with custom-made encoders, optical encoders inside of them. So that's why one motor is faster than the other one. But this is actually good because this gave me the idea and the need to make adaptive odometry implementation. It was 2 or 3 days for me. All the papers have some incompletenesses or some mistakes, and all the formulas should be checked. And yeah, but I think I can demonstrate now. So let's go to the demonstration. The other one, so these are the interface. These are the domain objects actually, position and movement commands. From the point of view of the client of the service. From point of view of the implementer of the service, they're low-level domain objects. For example, encoder positions, which are integrated or aggregated in a higher-level domain objects, which are called positions. Everything is with timestamp. Why? Because if I want to have acceleration or some time-based events, I need the timestamp. This was the hard-learned lesson. Okay, so it's Angular 2, excuse me. It uses some templating. This is actually a big component. It could be separated in smaller ones for position one, for the commands another. But now a monolith component, Angular 2 component in TypeScript. And actually, it uses Canvas for drawing the robot. And also uses the WebSocket, our reactive implementation. It's on the same address. It's actually hosted on the robot. Everything, WebSocket is hosted using ReactorNet together on the same address and port 80 with the web application with the static resources. Everything is hosted by ReactorNet. I can show you on Java site. And now we have 3 types of so this is the events, data events. These are the error and closing observers that we have defined for our reactive RxJS-based WebSocket implementation. And here is the submit to server. We just submit the JSON stringification of the JavaScript object, which is the command, movement command. And we have the position, so coming after starting the movement. How? Using some listeners, here, there, yeah, here, there, by subscription, using a reactive way, just by composing different producers, processors, and subscribers. Data flows instead of operations. And okay, there are some animations by Canvas. I'm not going in detail. So the server part is more interesting, but should I first, start it and after that go? So I close the client and go to the server. Okay, here it is. So I'm going to Java perspective. Okay, the code is not cleaned yet because there are different alternatives. I didn't clean all of them deliberately, but I will do this at the final version of the demo. So the main idea, we have other different domain representations using the domain language. What we have in the domain, we have a robot, we have Arduino, because the robot actually doesn't process the encoder data on Raspberry Pi. It's a Raspberry Pi-based robot. The main processor is Raspberry Pi. You can see here the Pi Raspberry. But there is a very small Arduino. I don't know if it is visible. It is here, Arduino. And there is also some accelerometer, gyroscope, and compass in 3D, which are hidden behind the Raspberry. And on the top, of course, is a TFT monitor. Okay, so this is the main idea. So let's see. First of all, we have here implementation starting from the low level from the encoder. This is the Arduino. It is a service that produces event, and I model it as a function. Function is like stream, but it's called, there are two types of streams now, fluxes and functions in Reactor. They changed their terminology. There was no flux half a year before. They also have monos, which are like promises. But okay, so it's a fluent implementation of stream API, of RX everything API. And what we do here, we have encoder readings, which are domain value objects, immutable objects. Where they are. There should be encoding. Here it is, yeah. So we have actually two values, left encoder, right encoder, and very important timestamp. Without it, you don't know the latency of the communication. It's serial communication, it's no real-time communication. And for acceleration, it's very important to know the difference in order to compute exactly the formulas. They're time-based derivatives. So that's why I need the timestamp. Next one. It comes by Arduino Leonardo because it is very easy way to interface your Raspberry Pi with Arduino in 5 volts. So your Raspberry Pi is in 3.3 volts, Arduino is in 5 volts. If you have sensors in 5 volts, you cannot connect them to the Raspberry Pi directly. You have to use some level shifter, or even better, offload all the processing in real-time dedicated controller like Arduino Leonardo. And it has a hardware USB, which means that if you mess something, you don't have to upload your bootloader in an exotic way because it's hardware-based USB to serial conversion. It's implemented in the microcontroller of Arduino Leonardo, which is different from Arduino Uno, the series of the microcontroller. They're at Mega, all of them, of course. So going from the domain objects to the service, which are actually producer of different, I use Broadcaster. Broadcaster is the preferred way to use hot event stream processing, to implement hot event stream. It's specifically designed for hot event streams. There are also different type of fluxes that are more usable for cold event stream processing, or you can convert a cold event stream processing by caching only several values, for example, or by using other primitives. You can convert a cold to hot event stream. But broadcaster is specifically good for hot event stream processing. It is very hot because they're coming fast rate from the encoders, all the events. Actually, not all of them, 50 milliseconds. I aggregate them first on the Arduino. I have some barrier in front of. Otherwise, it would be a really intensive computation for Raspberry. Okay, so what we do actually, we do first some processing. We have the data received. We now publish the event, but before publishing it, what we do some low-level buffer reading. Okay, and we publish our readings to next processing. Everyone who wants to know the encoder data should just subscribe. This is the beauty of publisher subscriber. It's at least for me, this is a very good way to separate concerns between producers and consumers, and to have loose coupling between them based on the value types which are immutable. Representation based on the same, or maybe not same, but translatable representation of the data. Okay, so let's go to the next. Next task is the position. How much time do we have? How more minutes do we have? Do you know? 5? Okay, so I should be fast. The next one is the position function. The function is again, it's consuming. It's actually, everything is organized at application level in the main class, which is called VoxDemo. And VoxDemo creates everything using factories. Actually, the first one is not using factory yet, but it will. It will use factory. Everything is created by using factories for position, which are providing a function of positions, which could be subscribed, and also for pure subscriber, which are command-based implementation of motor commands. Actually, we have very clear separation in this domain because motor could be commanded, encoders could be listened. We don't have a way to mix them, even if we want. But at higher level facade, we can expose them to the clients, both of them, using the same interface. But low level, they're implemented separately using different types of, for example, processors or concurrency implementations if we want different. Or if you want to have some recording in the database, there could be different. They share events using Stream API, Reactive streams, or WebSocket in case of the client with RxJS. So the streams could be continued from the server to the client without interruption, end-to-end reactive. This is the good part, I think. Okay, so let's go with the demo. We can start the main class. Do it from here. First of all, I have to switch to the other router because I didn't risk to use the. Okay. I switch to my own router. I hope that the robot is also. I can see if it is finding the router. Not yet. Yeah, I have it. Here is the address. Okay, I hope we'll connect. We just make another configuration, runtime configuration, by running as run configurations, and here we create a specific configuration. This is the way the plugin works. You just create separate run configuration. That's all. Nothing more, nothing less. And I have a certain already created configuration, which this is the IP address, the port that is used, and so on. And the user password should be also remembered. So now I hope they will connect. If not, I'll try again. Otherwise, I'll start it from there. Okay. Not from the first time. Let's see the second time. What? I have, no, I lost the internet connection, not the wireless. I don't have, the router is not connected to internet. But just a moment. Otherwise, I'll start it from there and show you from the robot. And the important part is also the client. Now it's launching, I hope. Almost launched. The next time it will. I don't know why, but the communication, maybe the timeout should be bigger. I didn't have time to change. There is no explicit parameter. Or maybe I didn't have found it. Okay, let's go. Please, please, please. No. Okay. I'll just restart again. The demo from here. Okay. It is rebooted now. And just in a minute it will start again. It starts fast. Okay, while this is starting, I can show you the other one. Okay, I think that this is the last program. I think it was moving in a square. But let's see if it was the last one. I don't know if it's visible. Yeah. Oh, why it's moving? Because it's programmed. It's programmed to see the surface, and if it doesn't see a surface, which is quite dark here, it thinks that it is at the end. It should turn, go back and turn. But we can use this. Maybe, but okay. Let's see if everything is now okay. Yeah, I think it's better. I have wireless connectivity. Let's see again. And this is the risks with the IoT and robotic demonstration. I think that if you have an idea how to mitigate the risk, I'll be very obliged. Now we started. The wireless didn't start before because I switched off the router. And yeah. So now we have the, I don't know if you can see here. This is the interface, which is embedded interface here. Do you see it or not? Not? Okay. Okay, it doesn't matter. The next I started from here, go to straight to A. This demo, we see it goes slightly in the other direction, but it compensates. It's adaptive. I'll show, you can see here, it's just 0.02 millimeters, according to the encoder's readings. Divergence from the straight line, from the target direction. And there are 3 millimeters in the Y in the position, in the end position, for 40 centimeters. Yeah, so I started on the left. It makes a curve which is computed. It's not just turning complex, but it's computed based on the parameters, the curving and the deltas of the XY. And the same could be done on the different direction on the right. Yeah, but I'll make it mobile because this was the idea to use the WebSocket. I can do from mobile, but I'll now demonstrate because it's not easy to see my mobile. I'll demonstrate from here, from a Chrome. This implementation of RxJS and Angular 2. I think I just have to open. So let me see. Here I have it. Yeah. So this is my WebSocket. Everything is served first by HTTP, the static resources. I can show you the net part. It's very easy. And after that, I hope it will start. Not yet. Why? Just a moment. Now it is. We risk with the demos. Yeah. We have XY. Oh, I have different resolution here. Okay, this is better. So I emulate mobile interface. It's using actually. Oh, I don't see my robot again. Let's see. Okay, please load it. Do I have my robot? Not yet. And the third time. Sorry. Let's see. It is better in this way. This attack cloud, which is just to have some space. Now the robot is here. And this is the mobile analog of the embedded interface. And we started, for example, going to the left. You don't have some space. You can see the compass. It's actually not the compass. The compass moves in the opposite direction. It's just a direction meter, the direction meter. Okay, let's have it here, going to the other direction. Let's see the difference. How much will be the compass after the opposite? How repeatable is the curve? This is the idea. It should be around 0, but how much around? We'll see. It's adaptive. It doesn't matter on the surface, or I can have something in front of the robot, and it will adapt. If doesn't in ice, how is it called? The word? Slip. It doesn't slip. It will track exactly and will compensate. For example, if one of the wheels is becoming slower because of the obstacle. Okay, so let's go. Yeah. You can see, of course, F12. You can see the WebSocket here. First of all, yeah, you can see. Okay, let's go forward. Yeah, you can see some messages. This WebSocket postings. Yeah, and that's all. Thank you. Thank you very much. If you have some questions, you may find me in front with the robots. I can show you even more details, or if you're interested in the details of implementation.